In this screencast, I want to demonstrate the idea of recycle by carrying out a calculation where we evaporate water from a potassium chloride solution and then filter out solid potassium chloride and then recycle the remaining solution, remix it with the feed. So what we want to do is carry out mass balances for this system. I've shown a diagram here, so what I'm going to do is pause and write down the information that we know and then create symbols for the values we need to calculate. So I've labeled them mass fractions that we know. I've also indicated in terms of symbols what it means that 84% of the total weight of the filter cake is crystals. So that means that this is the M4 over M4 dot, and M5 dot is 0.84. So notice what's leaving M4 dot, M5 dot, they're all together. It's just one wet filter cake that has crystals and then the solution with it. The unknowns are indicated with the purple rectangles. We may have to calculate, of course, some of the other values, but these are what the problem is asking. So the first thing we want to do is look at degrees of freedom and see if we have enough information. So let's do a degree of freedom analysis for the overall system. So let me pause and set that up. So if we were to draw a dashed line around the system and look at what streams enter, what streams leave. Of course, M1's entering, we know that. M2 is leaving, M4, M5. Those are our three unknowns. And then we can do mass balances on basically KCl and water or KCl and overall. And I've chosen overall balance just because it's a little easier to do to calculate. Either approach works, but there's only two independent equations. So the equations, KCl balance and overall balance. We need a third equation. The third equation is this information on the relation between M4 and M5. So let me just write that down as 0.84. So remember, three equations, three unknowns. Let's look at the balances. So first I'm going to do the KCl balance. And so that means KCl coming in M1, the mass fraction. So I'm using X as the mass fraction, just KCl. Mass fraction of water, of course, is 1 minus the KCl mass fraction, but it makes it a little simpler if I don't also write the mass fraction of water in the plots. So is equal to M4 dot, because its mass fraction of KCl is 1, they're all crystals, plus X5 times M5 dot. So that's the KCl balance. So I put in the numbers and I multiplied out 400 times 0.15 to give us 60. Now I'm going to use the equation here. Let me just write that down again and rearrange it when I write it down. So what I've done is bring the 0.84 to the left side of the equation, bring the denominator M4 dot, M5 dot to the right side of the equation. Now I can rearrange this to relate M4 dot to M5 dot. So I've simplified. Now I can substitute for M5 in my mass balance up here with this in terms of N4. So again, I'll pause, make that substitution. So I made the substitution, I simplified, I solved for M4 dot. I indicated purple, this is one of the values we are trying to find. It's one of the objectives of this problem. I can also solve for M5 dot since I know M4 dot. So I'm going to write that down, that M5 dot, and we're going to need this to do the subsequent calculations, 10.85 kilograms per hour. Well, now I can go back and do my overall balance system, and that's M1 dot equals three streams that are leaving, M2 dot, M4 dot, M5 dot. Only unknown is M2 dot, and so then I calculate for M2 dot. Now keep in mind, really not this many significant figures are justified. I've just indicated these so you can understand where the calculations came from. In reality, we only have two significant figures, so this number only 57, but I want to carry through the numbers in the calculation. So let's go back and look at the diagram. And what we want to do now is look at the crystallizer, since we have some of these flow rates and we have mass fractions, to do a degree of freedom analysis for the crystallizer, see if we can solve for M6, which is the remaining value we're interested in. And just emphasize the recycle stream, we know the mass fraction because it's the same liquid that's mixed with the crystals, so the mass fraction is 0.28 in both places. So I've indicated two unknowns as M3 dots. Let's look at the figure. Calculate M4 and M5. We know the mass fractions M3 dot, M6 dot are the only unknowns. And then we have two equations. I've written down the KCl balance, the overall balance, just because they're a little easier. Could instead have used the water balance, but only two independent equations. So let's look at the overall balance, and that is that M3 dot, that's what's entering. And we have the crystals plus the solution that's mixed with the crystals plus the recycle stream, and we've just calculated this is 56.96 and this is 10.85, and so M6 dot is our unknown. So we have a relation between M3 and M6. So now we want to do the KCl balance, and so stream coming in, mass fraction, M3 dot, stream leaving, so X4, of course that's 1, so it's just M4 dot since it's crystals, and then X5 times M5 dot plus X6 times M6 dot. So again, I'll pause, write down the numbers, and for M3 I can substitute in this equation. So I have an equation that the only unknown is just arithmetic. Now we can solve for M6 dot. We get a value 342.6 kilogram per hour. That's the third value we're interested in calculating. We don't need to calculate M3. We certainly can, but the problem doesn't ask for that. So we're going to stop there with calculation. Of course, again, this is perhaps written as 340 kilograms, two significant figures.